Hi class, today I will be discussing the topic of subsurface imaging and modeling of the current location of the subducted Farallon slab. We will discuss the image of the subsurface 3D rendering that you see here in further slides. Now let's go ahead and start from the Farallon plate's beginning. In order to gain a better understanding of the currently subducted Farallon plate, we would need to go back in time to approximately 55 million years ago, before continental basin and range extension took place on the western side of the North America we know of today. Towards the end of the Cretaceous, a massive oceanic terrain known as the Silesia, consisting of thalloitic basalts which were created on the Farallon plate, began to approach the western margin of the continent. As you see on the picture to the right, the little orange accretion over here is the Silesia, which is sitting on top of the Farallon plate, which is on the verge of subducting under the North American plate. Silesia, now in contact with the North American plate, begins to accrete, which causes the subducting Farallon plate to flatten underneath the North American continental plate. Once again, the image here demonstrates the Silesia on the verge of subducting under the North American plate, and you see that the Farallon plate is completely subducting under the North American plate there as well. Subduction begins to jump in a westward direction, which causes the underlying Farallon plate to break apart as it travels eastward. Now the Silesia accretion has completely subducted under the North American plate, and as it's accreted on the continental margin, the Farallon plate has actually broken apart, which has left the remnant offshore slab known as the Juan de Fuca plate that we know of today. So now that we got the Farallon plate's beginning out of the way, how exactly are we supposed to locate its current location in order to produce subsurface images of it if it's completely subducted? Behold dots. I'm kidding. This here is the Earth Scope Transportable Array, which is a dense network of state-of-the-art seismic stations that, from 2004 to 2015, migrated across the contiguous 48 states, which recorded the high-quality data needed to map the structure of the Earth beneath North America. With station spacing of about 70 kilometers, the transportable array data are extremely useful for detecting small earthquakes and mapping the structures of Earth's interior. The data gathered from the array has provided many geophysicists with crucial information needed to gain better insight of the Farallon plate's west to eastward subduction direction. Now, in order to gain better perspective of the interior of the Earth, after the transportable array has been installed, a good understanding of P and S waves is crucial. P waves are compressional waves that travel at high velocities and can travel through liquids, solids, and gases, while S waves are shear waves that travel at slower rates and only travel through solids. Now, scientists use this information to help them determine the structure of the Earth. For example, if an earthquake occurs on one side of the Earth, seismometers around the globe can measure the resulting S and P waves. As you see, the P wave on your left image is showing a compressional wave, while the S waves on the right image is showing your shear waves. Shown here are seismic imaging results from the US array, which were a contribution from researchers in a tectonophysics article. You see to your left-hand side a P-wave model. This is stretching from California on eastward, and an S-wave model, which is stretching from California, or Southern California actually, and eastward as well. The primary focus of this research was to understand the 3D geometry of the subducted Farallon plate. In order to do this, a technique known as tomography was used. This technique is used to measure and display the three-dimensional distribution of velocity or reflectivity of a volume of the Earth by using numerous sources and receivers. P and S wave models were obtained using multiple frequency tomography techniques. This waveform-based method interprets travel time and amplitude anomalies derived from the cross-correlation of observed seismograms. The data gathered in order to render these images was recent, regional, and were derived from body wave models. Now, the scattered wave image shows positive P to S conversion scattering potential in red, and negative conversion is blue. Tomography models all show fast velocities as blue and slow velocities as red, with the scaling shown on each section. So with that being said, the tomography velocity, which we understood to be blue, is telling you that this subducting plate here, which may more than likely, of course, be the Farallon plate, the subducted Farallon plate, traveled at a very fast velocity. The model shown here used seismic tomography that resolves the remnants of the Farallon plate subduction since the Mesozoic, approximately 100 million years ago, as input for defining its present-day structure. The evolution of the Farallon plate is very temporal, and the rendered seismic tomography shown in panel A and a prediction of tomography models in panel B display dynamic topography related to poorly known mantle buoyancy and viscosity. Plate motions are imposed as kinematic boundary conditions, allowing the mapping between dynamic topography and stratigraphic observations. The constraints involved to render the prediction models used uncertainties with stratigraphic data, including reconstructions of paleoshorelines, sediment isopachs, and borehole tectonic subsidence to get the best prediction results. The cross sections that you see in the images here show temperature anomalies, velocity vectors, dynamic topography in blue, which of course may be the actual Farallon plate itself, and longitudinal component of plate motion in red along the profile. The dashed blue line marks upper-lower mantle interface. What's actually very interesting about these prediction models, as you see in column B or in panel B, is their precision that is closely related to the actual seismic tomography of column A. Now, if we take a look at the Farallon plate, which is in blue here, during the Mesozoic, we can obviously see that it was a flat subducting slab. And the prediction model, with some constraints added, of course, actually renders almost a flat subducting slab here as well. Now, if we take a look at the cross-section from today, and as to where the Farallon plate currently lies, we can see that there is folding taking place, which is shown by seismic tomography, but the prediction model actually shows somewhat of a folding, subducting Farallon plate as well, traveling eastward in North America at quite lower depths. So this is basically telling you that if we work with seismic tomography and prediction models to make assumptions as to where the Farallon plate is actually located, this can actually lead to very precise data. So that ends my presentation of subsurface imaging and modeling of the current location of the subducted Farallon slab. I hope you learned something because I'm sure we all did.